Today we're going to take a look at the binomial theorem. By the end of this video, you should be able to construct Pascal's triangle, and you should be able to expand binomials using either Pascal's triangle or the binomial theorem. So, first, we have this pattern of numbers. This is called Pascal's triangle. It is named after the French mathematician, philosopher of the 17th century, Blaise Pascal. You might notice a few things about this triangle. It is symmetrical. Each row in the triangle begins and ends with 1. So let's take a look at how this triangle is generated, because it can continue on forever. To start with, the first row is just 1. The second row is 1 and 1. When we get to the third row, we can start to see how we can generate the rest of this pattern. If we take 1 and 1 and add them together, we get 2. Looking at the next row, we can see that 1 plus 2 gives us 3, and 1 plus 2 gives us 3. If we continue looking at the pattern, 1 plus 3 gives us 4, 3 plus 3 is 6, and 3 plus 1 is 4. So we can continue this pattern, making sure that we begin and end each row with a 1, and adding the two numbers above it to get the next number in the middle of each row. Now, if we want to continue this pattern, we would start the next row with a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And then we would end with a 1. And we can continue this pattern indefinitely. But the important thing about this pattern is that it gives us a list of coefficients for binomial expansion. So here's what I mean by that. If we have x plus y to the 0 power, well, anything to the 0 power is 1. So our answer would just give us 1, which is the top number in the triangle. If we have x plus y to the first power, that is just x plus y. So the coefficient of both x and y is 1. And there are 2 1s in that row of the triangle. If we look at the next row, if we have x plus y squared, if you multiply it out, x plus y times x plus y is x squared plus 2xy plus y squared. So the coefficients are 1, 2, and 1. If you continue this pattern, the next row gives us the coefficients for x plus y cubed. We would have x cubed plus 3x squared y plus 3xy squared plus y cubed. The next row gives us the coefficients for x plus y to the fourth. The next row gives us the coefficients for x plus y to the fifth. This row that I wrote out gives us the coefficients for x plus y to the sixth. So in general, the row 1 n and the ends in n1 gives us the coefficients for the expansion of x plus y to the nth power. So let's take a look at how we can use this. If we want to expand x plus y to the 5th power using Pascal's triangle, that'll be much faster than having to multiply out x plus y times x plus y times x plus y times x plus y times x plus y by hand. So, when we are raising this binomial to the 5th power, we can look at the row that starts with 1 and 5 to get our coefficients. So our coefficients are going to be 1, 5, 10, 10, 5, 1. So I'm going to write those down. Now the other thing we have to figure out is the exponent for the variables. So let's start with the first part of our binomial, which is x. You are going to start by raising that to the nth power, so in this case the 5th power, and in each term you are going to decrease the exponent by 1. Then for the second part of the binomial, in this case y, you are going to start with y to the 0 power and increase the exponent for each term. Then you add these together to get your polynomial. So if we simplify this, you have x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the 4th plus y to the 5th. And that is our polynomial. If you prefer to multiply it all out, by all means go right ahead. The one thing to take note of is that in each term, the sum of the exponents is always the same. 5, 5, 5, 5, 5, 5. And it will always add up to whatever n is, whatever power we are raising the binomial to. Let's take a look at another example. If we want to expand 2x minus 3 to the 4th power, we want to start by looking at the row in Pascal's triangle that starts with 1, 4. So we have 1, 4, 6, 4, 1 as our coefficients. Now, this one's a little bit trickier. We need to raise 2x to the 4th power Then we're going to take negative 3, raise that to the 0 power, and increase the exponent for each term. And add the terms together. So for our first term, when we have 2x to the 4th, we have to remember to raise 2 to the 4th power and x to the 4th power. So we end up with 16x to the 4th. In the second term, we have 4 times 2 cubed times negative 3, which gives us negative 96x cubed. In the next term, we're going to have 6 times 2 squared times negative 3 squared, which gives us positive 216x squared. In the next term, we have 4 times 2 times negative 3 cubed, which will give us negative 216x. And in the last term, we just have negative 3 to the 4th power, which is 81. So this is the expansion of x squared minus 3 to the 4th power. So this method works for fairly small powers of binomials. But if you're asked to find the 217th power of a binomial, you would have to write out a whole bunch of rows of Pascal's triangle to get to the row that starts with 1, 217. So there is another way to do this. We could use the binomial theorem. If you remember back to Algebra 2 when you learned about combinations and permutations, this NCR here is the same as the combination N choose R. It can also be written in this notation or using the combination formula here. Either way, this will give you a coefficient. So, if you need a reminder to find the combination in the calculator, NCR, you go to Math, you go over to Prob, and you click number 3. This is read as N choose R, and that will give you the coefficient. It is important to note that this R here in the combination is one less than the term you want. So for example, if you want the third term of the polynomial, R would be 2. And as I mentioned earlier, following these rules, the exponents of x and y will still add to n. So let's take a look at a few examples where we can use binomial theorem instead of Pascal's triangle to find a specific term. If we want to know the third term when n is 5, we can start by using the binomial theorem. If we want the third term, then that means we are doing 5 choose 2, r is going to be 2, times x to the 5 minus 2 power times y to the second power. So let's go to our calculator and figure out what 5 choose 2 is. If you go to Math, go over to Prob, and choose number 3. 5 choose 2 is 10. So we would have 10x cubed y squared. And we can go back to our previous example and verify this. So if we go back to problem number 1, the third term is 10x cubed y squared. If we want to know the fourth term when n equals 10, n is 10, r is 1 less than the term you want, so r is going to be 3. Then we have x to the 10 minus 3 and y cubed. Again, if we go to our calculator and we want to figure out what 10 choose 3 is, we have 120. So this would be 120 x to the 7th y cubed. We can also use the same method with slightly more complicated problems. If we want to find the sixth term for a plus 2b to the 8th, we know that n is 8 and r is 1 less than the term we want to find. So r is going to be 5. Then we have a to the 8 minus 5th power and 2b to the 5th power. So if we go to the calculator, 8 choose 5 is 56. A cubed times 2 to the 5th power is 32. B to the 5th. And then if we multiply 56 and 32, we get 1,792 a cubed b to the 5th. The other option is to continue on with Pascal's triangle until we get to the row that starts with 1 and 8, and then figure out what our term would be using Pascal's triangle. Lastly, if we want to find the term for a plus 2b to the 8th that contains a to the 6th power, we need to think about this. In our expression, the first term would have a to the 8th, the second term would have a to the 7th, the third term would have a to the 6th. So we are trying to find the third term. N is 8, and r is 1 less than the term we want to find, so 2. We have a to the 8 minus 2 power times 2b squared. So if we go to the calculator, 8 choose 2 is 28. A to the 6th times 2 squared is 4, b squared. So we end up with 112 a to the 6th b squared. And that would be the term that contains a to the 6th.